welcome to this afternoon's tutorial on counterfactual inference. It's a great pleasure to introduce Professor Susan Athey, who is the Economics of Technology Professor at Stanford Graduate School of Business, and she previously taught the economics departments of MIT, Stanford, and Harvard. She's had many awards and accolades, and I won't cut into her time by telling you about all of those, but she was elected to the American Academy of Arts and Sciences in 2008 and the National Academy of Sciences in 2012. Her research focuses on economics of the internet, online advertising, the news media, marketplace design, virtual currencies, and the intersection of computer science, machine learning, and economics. And I think there's a lot of interest in causality and counterfactuals, etc. So it's great to have her here. Just before we start, there are two things we need to handle administratively. One is that there will be a break at about 55 minutes. So there'll be a 10-minute break then, and we'll want you to come back afterwards. And the other one is that I think that it's probably best if we leave the questions to the end. Just, by the way, when there are questions, we'll have to use the microphones here because this is a large room. But I guess I'll let Susan, get on with her tutorial and also handle that. So thank you.
So thank you so much for having me here. It's a real honor to be able to give the tutorial to such a terrific and large audience. One of the things that I'm finding as I'm going out and speaking about this topic is that in some ways it's gotten harder to give tutorials and lectures over the last few years, because when I started working on this topic maybe 8 years ago, from a machine learning perspective, there was a sense that only a very small part of the machine learning community was really thinking about counterfactual inference or really even thinking about the words. And very little of the economics and social science community was thinking about machine learning. So if I went to an audience that was mostly one or mostly the other, I could pretty much count on people knowing a lot about one thing and not so much about the other. One of the really exciting things that's happening now is that a lot of these literatures are coming together, and there's a lot more interest and knowledge out there. So today I'm going to try to do my best to kind of hit a little bit of both worlds. I'm going to start from the beginning and talk at a high level to people who aren't that familiar with the topic, because I hope some people have come out because they're curious. I'm also going to try to give some insights to the more advanced folks, and we'll see how that goes. One thing, if you're interested in more, I should say I haven't given that many references throughout my slides, but then when I post them, I'll have some references at the end. But just for those who are interested, I did a 2-day lecture series for the American Economic Association, and there's videos and slides available, as well as 2 days of lecture notes from a much longer tutorial. I also have links to several survey papers there and so on. So if you're interested, please, you can Google Susan Athey, AEA, that's American Economic Association, and you'll find that all that material there. And would love to answer any questions via email as well. So I've been working myself on using data to answer counterfactual questions for most of my career. I started working in auctions. Actually, I started working on auctions when I was about 17 in 1987, and I was an undergraduate. At that time, nobody really cared about auctions, and we were, even in economics, we were relatively early in using data to do counterfactual estimation. And that was a very exciting time. I came only to machine learning in around 2007 and 2008, when I went to work as consulting chief economist for Microsoft for a few years, and particularly focused on the Bing search engine. And there I met a fantastic set of collaborators from the machine learning community, from Microsoft Research, the engineers building the search engine, and so on. And one of the really interesting things that I encountered was that I felt like we were actually needing to solve a lot of counterfactual problems, yet a lot of the folks from the machine learning community didn't really have a good language to talk about that. And so at the beginning, we had a lot of sort of culture clashes of people insisting that, one thing was possible, or I said, well, I thought that was impossible without running an experiment. And, we had difficulty sort of communicating. But then those early debates and interactions really bore fruit later as they really working with some of the smartest people in the world, all attacking an applied problem and really trying to get to answers, helped us, I think, all learn from each other, and it really embarked me on a new research agenda. I had been more of on the applied side, really using data to help make decisions and to do counterfactual estimation for specific problems. But I felt like this whole area was just so wide open that there was, like many of you as well, the world changed and we all dropped everything to come and think about machine learning, and in my case, the intersection of machine learning and causal inference. And this has gone from being a very small literature to really a much bigger literature in the last few years. It's growing very quickly. And so even my survey of a year ago already is getting out of date. So let me start with a big motivation for people who think about artificial intelligence broadly. And I want to talk about really two sets of issues that I think make sort of causal inference, counterfactual reasoning, kind of must know, must understand concepts for artificial intelligence. The first is that we all are seeing that there are some gaps between what we're doing in our research and what firms are applying. And of course, there's all these amazing success stories of Google Images and so on. But actually, even at the top tech companies, there's maybe less adoption of machine learning and artificial intelligence in some systems than you'd expect, given that all the people there are inventing it and embrace it. And so when we think about some of the impediments to adopting machine learning and artificial intelligence in applications, there's a whole sort of grab bag of issues. And each of these issues is the subject of tutorials and workshops in and of themselves. But to me, they're all pretty interrelated. So we typically, if a firm is going to dump their old simple regression credit scoring model and put in one based on a black box machine learning algorithm, for example, they're going to have some reservations. They're going to worry about what happens when they use a black box algorithm. And the first thing that comes up is, well, is this interpretable? How would I understand, if it was working and why it was working? And you might say, well, why do they need to understand it? Well, because they're going to make decisions, and actually it might take 5 years for the loans to be repaid or not repaid, so it's going to take some time to really get feedback on whether they work. And so one reason that firms and economists historically use very simple models is that we were trying to come up with things that we could understand because we were typically in a data-poor environment and in an environment where it was pretty hard to know just by looking at the data whether we were right or wrong. And so if something's interpretable, you can reason about it. And actually, if you were an applied economist, what you would do with a research paper, an empirical paper, you guys will be really amazed by this, but we would often spend 4 or 5 years getting an empirical paper published. And we might present it 25 times and sit in a room of smart people for an hour and a half, and everybody would beat up our models and try to reason about whether they made sense. And then we would improve them and think about implications, and in this edge case and in that edge case, what would the model say to see if they were reasonable. And so there's that kind of reasoning is harder to do in a black box. Closely related to that are issues of stability and robustness. So, if we use Twitter data today to decide if someone's creditworthy, that may be difficult because maybe people who were on Twitter 3 years ago are different from people who joined Twitter during the presidential election, and maybe it's a different signal of what kind of person you are year by year, how your Twitter usage is changing. So things like stability are also important for applications. And that, again, is related to robustness as well. A similar concept, transfer learning. So we might estimate a model in one setting and want it to apply in another setting. There's a very exciting machine learning literature around fairness and discrimination. And again, with black box models, we have to figure out ways to assess them and see if they are discriminating or if they're unfair in certain ways or if they're making generalizations that we're uncomfortable with. And I think there's a bigger picture. We're building a big initiative at Stanford on human-centered artificial intelligence, and I'm involved in organizing that and leading it. And one of our missions is to create more human-like artificial intelligence. But to me, what does it mean to be human-like? One big aspect is that you're going to make reasonable inferences, reasonable decisions in scenarios that you haven't seen before. And again, that's going to be part of causal inference and counterfactual reasoning. So my argument is going to be that actually all of these desiderata are satisfied sort of by design in a causal model. Now, I'm not going to argue that all problems can be solved or that I can solve all problems, because actually it's really hard to actually implement a causal inference framework and to get credible estimates. But the causal inference framework actually gives a framework for understanding and in at least a guideline for how you would address all of these issues. So in a causal inference framework, really your goal, the stated goal, is to learn a model of how the world works. And that can be something simple like, what happens to your body if I give you a drug? That's like a simple treatment, a simple intervention. It can be like a production function, so I'm trying to understand the mapping from inputs to outputs of a firm. It can be something like understanding, what would happen if I raise the price, how will consumers change their behavior? And it might even be something as complicated as doing inference about what happens if I change the rules of an auction. That's something we thought about at the search engine. What would happen if we moved from a generalized second price auction to a Vickrey auction? And in my early career, I worked on timber auctions and looked at comparing first price sealed bid auctions to open ascending auctions and second price auctions. So we might want to do inference about what happens when we change the rules of the game. And indeed, economists have applied these techniques not just to timber auctions, also to treasury bill auctions and online advertising auctions. So these are the kinds of questions we want. Now, in general, within economics, within empirical economics, I would say like 95% of the empirical work is in the causal inference framework. So almost all of the work that is done in that field is trying to get causal effects. And even though everybody agrees on that goal, there's huge arguments about how to approach the goal and whether any particular paper achieves the goal. And that's partly because you can't just look at the data and see whether you got the right answer for causal inference. It's almost always assumptions, unless you have repeated experiments. And of course, that's something that we look for. Ideally, you would have a world with lots of experiments. So you use data from some experiments, and you can see how you do on other experiments. But you don't always have that scenario, especially if you've never done something before. And so one of the things that we spend a lot of time worrying about is that the impact of an intervention can be context-specific. We worry about external validity, that I might learn something in this setting, but it doesn't generalize well to other settings. Now, that's not a problem with the framework, because in principle, you can write down all the things about the context that affect, whether the drug works or whether giving children bed nets or lowering class size is a good idea. But in practice, of course, it's very hard to estimate all of those things. So again, this comes to be a practical problem, but at least we have a language and a formalism to talk about what goes wrong when we try to generalize. So our model would map context and interventions to outcomes. And again, we would then have a formal language to separate correlates from causes. So think about something like gender. If you say, OK, here, I'm a 47-year-old woman with 3 kids, how much do I know about artificial intelligence? Maybe if that's all you know about me, your guess is that, probably not that much. Your average 47-year-old woman with 3 kids in the United States probably doesn't know that much about artificial intelligence. Although I would say my Border Patrol person entering at the airport asked me if I was a natural language specialist, and I said no, I was doing causal inference. So, and he complimented me for being original. So, maybe everybody knows something now. But, of course, we have lots of covariates that can be predictive of people's attributes in the absence of other information. But you might want to think about what would actually cause me to know something about this subject, and it might be my computer science degree from undergrad, it might be all my publications and research that I've done, and those are the real causes of my expertise. So the ideal causal model is by definition both stable and interpretable, because it's a model. And so when we write down a causal model, we are giving it an interpretation. When I say, here's a drug, I want to estimate the effect of the drug, That's interpretable. It's a well-defined mathematical object. You can argue, when I show you a number and I say, hey, this drug makes you 10% better, you can argue about whether I've actually measured that properly and whether I have an unbiased estimate and whether there were confounders and compliance issues and all sorts of other problems. But conceptually, the thing I'm estimating, my estimand, is perfectly interpretable. It's just a problem of whether I've actually succeeded in doing that in practice. Transferability, well, in principle, if I understand the impact of a treatment and I understand how the context changes the interaction of the treatment, then I can transfer it to any new environment. And again, with fairness, many aspects of discrimination relate very closely to sort of correlation versus causation. And the fact that we're doing sort of statistical discrimination as Bayesian human beings, we're all Bayesian, right? So as Bayesian human beings, we update. If we only have a few pieces of data, we draw inferences based on that data. And our models are drawing inferences from data as well. And if, say, there's too many covariates and we do some regularization, we're going to load up onto some attributes, even if those aren't actually causal. So I would argue that, in some sense, like, a lot of the world's problems could be solved if we could all just estimate causal models all the time. But as I mentioned, I'm not going to argue that I or any of my friends can solve all of your problems, because it's actually really, really hard to do causal inference. And there's all sorts of challenges that remain. Probably the biggest one, and the one that we've struggled with for decades in economics, is that we just don't have the right kind of variation in the data. Until recently, firms didn't run many experiments. And so, if we wanted to understand what would happen if a firm changed its price, an economic consultant might go to a firm and say, all right, show me your data. And they're like, well, we've kept our price of this cereal, constant for the last 3 years. You're like, OK, so how am I going to figure out what would happen if you change the price? That can be really difficult if they've never changed the price in the past. And so there might be lack of variation at all. Or then it might be that the variation that they do have is due to confounders. So suppose I wanted to try to understand the impact of a hotel raising its price. I could go out and count people going into hotels, and I could scrape prices from hotels.com to see what the prices were. And I would see prices change, and I would see the number of people in the hotel change. But what I would also see is that when the prices are high, is the hotel full or empty? Full, right? What are the prices like right here, right now? They're high because you guys filled up all the rooms, okay? And that's because the hotels are using algorithms to set their prices, and in particular, when it looks like there's a big conference coming to town, of course, there's discounts and so on for some people, but for a regular business traveler who wanted to stay here this week, they're paying a very high price. So there's variation in the data. There's lots of price changes in the data, but it's not the right kind of variation. It's not experimental variation, and in particular, it's moving sort of one for one with demand, and so it's hard to know what would happen if I changed my algorithm to set a higher price in every state of the world. We also typically have a hard time observing all the context or getting enough data about all the context in order to understand treatment effect heterogeneity. And then also, analysts often have a lack of knowledge about the model. And again, this problem we struggle with in economics for the last few decades is that we often were in a data-poor environment. So we've had people working on problems like dynamic games between firms, or dynamic decisions that workers make about unemployment decisions, and so on, what unemployment insurance, or whether to take a job. We've been building these models for decades, and they've worked pretty well. This is inverse reinforcement learning. It turns out like several of the components of AlphaGo are basically mapped right onto techniques that were used in the 1990s in economics. But those methods didn't sort of change the world. Firms didn't replace their store opening managers with AIs because it was actually pretty hard. Our problem wasn't that we didn't know the right techniques. The problem was we didn't have enough data. And we didn't have enough variation in the data to really understand, what would happen if Walmart opens a store here and doesn't open a store there, if Target opens a store here, and so on. So the problems are really not conceptual problems. The conceptual framework is solid. The problem is, how do we implement in practice? Now, the very exciting thing is that now we have firms that are running tons of experiments. And we're interacting with humans in a digital environment. So actually, we're creating environments with lots and lots of variation, lots and lots of data, lots and lots of context. So the reason this got really exciting for me is not because there was some groundbreaking new philosophy. In some sense, we've had the philosophy for a very long time. What was exciting is, wow, we can actually do something with it. Outside of a few very special circumstances, we can do something credible. At the same time, I'm much more optimistic about the ability of all these techniques to work in settings that have lots of experiments and lots of randomization, like the tech firm settings, than I am for settings that don't have that. So building an AI to run the central bank or to make opening and closing decisions for Walmart, I think is much, much farther off than some of the other problems. So now kind of drilling in a little bit more deeply into more like true AI algorithms. So I'm going to use as an example in this talk sort of contextual bandits, because that's a very simple, tractable example of a very simple artificial intelligence algorithm. So multi-armed bandit is balancing exploration and exploitation to try to figure out which arm is the best to pull, which is the best treatment arm. And a contextual bandit understands that in different states of the world, there might be different optimal treatments. So if one application I'm looking at is recommending charities, recommending people give to charity when they come in to check out with PayPal. So in that case, the contextual information might be which websites they were coming from and maybe something about their purchase history. And that might help me recommend a charity as well as a motivational message to the person. And I'm going to want to learn online, learn over time, what the best arm to pull is. So that's a simple example. Of course, reinforcement learning and the robots climbing the wall and the people playing video games and so on are more complex examples. But in all of these cases, what the AI is doing is they're selecting among alternative choices. And they therefore must have an explicit or implicit model of the payoff from alternatives. And that's a counterfactual model. And that's not surprising that, especially the people working in the contextual bandit literature have been sort of closer to the statistical literature on causal inference than some other parts of machine learning, because you recognize that actually, if I'm running experiments, I'm thinking about counterfactual reasoning. Of course, in the initial phases of learning, you have limited data. So a lot of the theory in this literature is just like, OK, n goes to infinity. Everything is good. We've learned the best thing eventually. But if I'm running survey experiments or if I'm trying to get people to vote or whatever, I actually often don't have enough data. Treatment effects are often pretty weak. I'm often very underpowered. So actually, you really do care about what happens in the initial stages. And it's important to be a good statistician. So I would argue inside sort of every AI of this type is a statistician performing counterfactual reasoning. You haven't necessarily written it down or spelled it out, but that must be what you're doing, of course, unless you just programmed all the heuristics in to start with. But an AI that's exploring and learning about the world is going to be building a model from its past data and drawing inferences about the best action to take in the future. And I think then it's sort of tautological that you would rather your AI be a good statistician than be a bad statistician. Okay? And so, of course, at the beginning, we're going to be really excited about all of our AIs that are simple statisticians. I won't call them bad statisticians, but they're simplistic statisticians because they can do really cool things. They climb over walls, they play video games, they run mazes, and so on. But eventually, we're going to hit some diminishing returns to that. And then for the next round of improvements, being a good statistician is going to be very important. And indeed, I've seen in practice in applications of bandit algorithms that they can kind of go off the rails due to biases that are very predictable if you think from the perspective of causal inference. And that's basically just, you're going to tend to, in a region where you think that arm A is good, you're going to pull arm A a lot. In a region where you think arm B is good, you're going to pull arm B a lot. And then as a statistician, you're going to end up having sort of biased data because arm A is going to be, you're going to be getting high outcomes for arm A in the region where arm A is good, and high outcomes for arm B in the region where arm B is good, and you're not going to necessarily extrapolate well to the rest of the distribution. And we have, luckily, great techniques for dealing with that, but they haven't been adopted so much, so that's something that I've been working on with co-authors. All right, so in the next little section of my talk, I'm still going to be very conceptual, and I'm going to talk through a couple of different types of counterfactual inference. And I should say that this is one thing that gets very confusing, especially in interdisciplinary audiences, because you say the words, and everybody thinks it means something specific, but perhaps something different. And I would say we have good history on that in economics because we've been having arguments, huge clashes, wars, debates, fights between different leaders of different approaches to causal inference over the last decades. So just because you agree that you want to think about causal reasoning doesn't mean that you agree about how you should write it down, whether you should use equations or this notation or that notation. And also doesn't mean that everybody agrees on what the most interesting questions are. I think a lot of that noise can be dealt with by just realizing, actually, there are lots of different questions. There are usually multiple ways to write down the same thing. And we just need to be a little more precise about what we're talking about. And there's really no reason to fight about mathematics. We just have to write down correct mathematics. So the first type of counterfactual inference, especially that's very popular in the social sciences and biostatistics, is what we call in economics program evaluation, or more broadly, treatment effect estimation. And so the examples of the kinds of questions we've been worrying about for a long time are things like, what was the impact of raising the minimum wage? This is a very famous paper from several decades ago trying to look at the impact of changing the minimum wage, and you're comparing New Jersey to Pennsylvania, and you try to use one as a control for the time trend and the other to understand the impact of the minimum wage. So these types of problems have been hitting us for a very long time, even in a world where we didn't have a lot of data. Training programs have also been a really important and active area. Big literatures on what's the effect of reducing class size for kids. In the more modern economy, one of the biggest applications of this literature is advertising effectiveness. And there's an economist friend of mine at Netflix who's doing a ton of this, and basically, Netflix is amazingly good at estimating the return on investment of their advertising using a lot of randomized experiments and also bringing together observational data with experimental data. And so we have questions like, did the advertising campaign work, and what was the ROI? And these are very hard questions, actually, because as some of my colleagues pointed out in a research paper, that basically most advertising experiments run by large firms are underpowered. That means you don't have enough data to even tell if the campaign worked, even if you had a perfectly designed experiment. And you certainly can't reject, if you're lucky, you can just tell whether the advertising worked, but it's often almost impossible to tell if there was a positive return on investment, whether it was worth the money. So we really need to be careful with our statistics about those problems because the signal to noise ratio is such a problem. Another really active area of the political science community is get out the vote campaigns. And actually, again, since the 80s, we've been running these large-scale experiments that used to do big mailings. There was a famous study where they sent people letters, and your voting record in the US is public, so they sent people letters saying, we're going to tell your neighbors whether or not you voted. And they compared the effectiveness of that to other types of messages and found that telling people they were going to tell their neighbors whether or not they voted was a very effective way to get people to vote. And so we would want to estimate, first of all, do these campaigns work? And now the more modern versions of these, and these really are just getting rolled out in the last couple of campaigns, are more personalized policies, and these campaigns are starting to use things like bandits to learn the best policies. And what's an optimal policy assigning workers to training programs? So in this world, the goal is to estimate the impact of an intervention. And this literature generally focuses on low-dimensional interventions. There's extensions to more complex cases, but 95% of the literature is about a binary treatment. So a drug or raising the minimum wage, but one change in the minimum wage. The estimands, the things that people are interested in learning, are what was the average effect? Just did this thing work? The more sophisticated, more recent versions look for heterogeneous effects. So for whom did it work? Because that will tell me in the future, who should I send a mailing to try to get them to vote? And also more recently, a lot more emphasis on estimating optimal policies mapping from people's characteristics to their assignments. And a big emphasis in this whole literature is confidence intervals. So because we can't observe the ground truth, and because there's often pretty noisy effects of most treatments, and experiments and so on are expensive, we're typically really worried about sampling variation. We're typically really worried about whether the effects we're finding are spurious. And we're also really worried about bias. We're worried about things that we're actually going to say something's good when it's actually bad. And so there's a huge emphasis on estimating an effect, estimating it consistently, and putting confidence intervals around it. And just to get published in an economics journal, that's basically table stakes. That's one reason people have been slow to adopt a lot of machine learning methods, because basically people don't know what to do if they're going to write a paper where there's not a coefficient estimate, an asymptotic normality theorem, and confidence intervals. So that's been part of my research agenda, is to provide those for economists on machine learning methods so that they can actually start to use them. Now, there's a big important point, which I want to just pause on for a moment, which is that we don't actually know the ground truth. And that's really a big difference between supervised learning and causal inference. So I could think about, what's the treatment effect for each of you of giving you coffee before you walked in? Well, I could try to estimate that effect, but of course, people for whom coffee is effective tend to have chosen coffee, and people who don't normally drink coffee and stay alert without coffee didn't get coffee. So if I just looked at the correlation in the audience, I wouldn't be able to get that causal effect. And if I held out 10% of you, that wouldn't really change anything. I could find a big positive correlation between, actually in this case, I might get a zero correlation between coffee and heart rate. I might get that in the training set. I would also get it in the test set, but that wouldn't tell me anything about whether I got the right answer about what would happen if I force-fed you coffee. Okay, so we don't have treatment effects stamped on our forehead. We don't have a held-out test set that tells us whether we got the answer right or wrong, and that's one reason that we focus a lot on theory. So instead, this literature focuses a lot on designs that enable what we call identification and estimation of these effects. So first of all, this whole literature tends to focus on treatments that have been observed in the past. So we have a data set. Some people got the drug, some people didn't. The problem is that maybe they weren't randomly assigned. Random assignment is, of course, the gold standard for figuring out causal effects. But what happens if you need to make a decision and you don't have that? So this literature focuses on what we call designs, different designs that would allow you to learn about causal effects even without a randomized experiment. So one category are natural experiments, and those are called instrumental variables is one example, and I'll come back to that. Also, unconfoundedness would fall into this under some assumptions, and I'm going to go into those in some detail. Three others that I won't go into today, but that are also very, very popular for drawing causal inference in the social sciences. One is regression discontinuity. So you compare people near a boundary. So for example, I want to figure out the impact of being in school A versus school B. I compare people on opposite sides of the street where there's where the school district boundary is. And I say, well, their neighbors were similar, their houses were similar in price, all that was different was the school they went to. Or if there's a test score criterion for getting into a school, we look at people whose test scores were just below the cutoff. So we look at people whose incomes just qualified them or just didn't qualify them for a program and so on. Of course, there can be a lot of problems with these as well. Each of these examples I just gave, you can think of reasons that would go wrong, but that's a very popular type of strategy. And in fact, for tech firms, you can think about designing these types of experiments. So Hal Varian, Google's chief economist, recently wrote a paper with Art Owen from Stanford about this, and he was sort of arguing that, hey, like in YouTube, they give them free T-shirts if they get enough likes on their video. So instead of just having a hard cutoff, like if you get more than 10,000 likes, I send you a T-shirt, instead, I should take all the people near 10,000 and randomize them, and then I would get even more statistical power from that program. And I could actually learn whether T-shirts help or whether Google's wasting their money sending people all these T-shirts. So that's a regression discontinuity design. The difference in difference design, and it's closely related to looking at longitudinal data, a classic example of this would be like, say Kansas had this tax reform. So of course, the world is changing, the economy is changing, you're coming out of a Great Recession, but you can look at states that are a lot like Kansas and look at their time trends, and then Kansas at some point passes tax reform, and you can see how its outcomes kind of go downhill relative to the time trend that was established by the other firms. And this area is one that's seeing a lot of activity right now in terms of bringing together machine learning methods, particularly matrix factorization methods and causal inference methods. And that's something I have some papers on you can find on my website. I'm not going to talk about that anymore today. OK, approach 2. And I should say in economics, the people who do approach 1 and the people who do approach 2 generally are not friends. They kind of argue a lot. So I've done both in my career, but not that many people kind of, especially historically, did both. Now it's becoming a bit more common. So structural estimation, the way the structural estimation people would say is that they make more assumptions, but they also answer more interesting questions. So at some level, the first approach is only good for comparing people who got something and people who didn't get something, and you can just measure outcomes. The goal of structural estimation is more than that. It's to be able to think about worlds we haven't seen before, and also to say something about welfare. I want to understand, if I raise the price, what's that going to do to consumer welfare? What's that going to do to firm profits? Okay? And these kinds of models have also been used for decades in antitrust cases. So if Staples and Office Depot want to merge, some economist is going to get paid hundreds of thousands of dollars to write a report building a little model that says, well, if these two merge, this is how they're going to change their prices, and that's what it's going to do to consumer welfare. The area that I worked on this most historically was in auctions, but I'll show you an example at the end of doing that now. I'm working with David Bly on models of pricing. So what would happen to firm demand if price increases? What would happen to prices, consumption, and welfare if two firms merge? What would happen to platform revenue, advertiser profits, and consumer welfare if Google switched from a generalized second price auction to a Vickrey auction? And that's a change actually that Facebook made at some point, and those of us working in this literature discussed that at the time. Okay, so how does this work? Well, our goal is to estimate this impact on welfare profits of participants in alternative counterfactual regimes. And these regimes may never have been seen before. So how could you possibly do that? I remember when I first explained this to friends at Microsoft 10 years ago, when I finally convinced them of what I was doing, they're like, you're smoking dope. That can't be science. How could there be science where you're claiming to make a prediction about a world you haven't seen before? How could you possibly do that? And the answer is you can only do that with some assumptions. But in some cases, you can make assumptions that make a lot of sense. And of course, your artificial intelligence agents are going to have to do that. They have to reason about worlds they haven't seen before. And so we're all kind of in this business. OK, so you need basically a behavioral model for the participants. You need to understand why the agents in your data are doing what they're doing. So for example, I could assume that when you go in the supermarket and you choose a cereal, you're choosing the one that maximizes your utility. That's a behavioral assumption. You chose the one that maximizes your utility. Of course, I could also imagine that you don't gather all the information or that you're sloppy. There's lots of other assumptions I could make. The starting behavioral assumption we would make is that you're maximizing your utility. So if there were two cereals offered at different prices, if you took one of them, you must have liked that better than the one that you didn't take. And from that, I can learn something about your preferences. We call that revealed preference. Your choices reveal something about your preferences. Of course, we still need designs that enable identification and estimation. So for example, if I want to learn about people's responsiveness to price changes, I still need there to have been price changes in my historical data. And I still need the right kind of variation, say quasi-random variation in the data. But I'm going to go farther with these models. I'm going to rely on the behavioral model to estimate what you would do in different circumstances. If I suppose I watch you go to the supermarket over 18 months, which I do in some of my papers, over time, I'm going to learn how you feel about prices. So I can predict what would happen if a price changed. I can say that you're very price sensitive. If this price goes up, I've never seen you with that price before, but I don't think you're going to buy. And so in this particular data set, we have prices changing every week. And so we do hold out data where prices change. And we show that, indeed, we do a good job at figuring out who buys and who doesn't buy when the price goes up. Now, I'm not going to be able to talk about this too much today, but there's a really lovely paper by a young economist at Yale named Agami. And he actually does a nice job. He has a little paper that's basically artificial intelligence as structural estimation. The paper is written for economists, and it's basically showing how things like AlphaGo are using what would be known in machine learning as inverse reinforcement learning, and what we've talked about is dynamic programming, value function iteration, policy function iteration, and so on in economics. Now, there's some question about how much value making that mapping works. In the examples I'm going to show you today, I'm going to show you how I think I can make AI better by being better statisticians. We have some ideas about how I could make AlphaGo better by also thinking about it the way that we've thought about it, but I think it's a little bit less clear, whether or not those improvements will materialize and how important they will be. So another type of counterfactual inference, causal discovery or learning the causal graph, is about uncovering the causal nature of a system. So, and this actually is mostly attributed to Judea Pearl. And this is often what machine learning people, when I say I'm working on causal inference, people often think I'm working on this. This has actually not been the main focus of economics, often because in economics, we're just answering like a much more simple question. We want to know, like, did the minimum wage change work? And we already understand, we have a model, we have an economic model that, of what causes what. That if I raise the price, people won't buy my stuff. If I raise the minimum wage, certain things will happen. So I kind of understand qualitatively how the world works, I just don't know quantitatively. And so in economics, we've focused a lot on just estimating the magnitude of things and getting really precise estimates and unbiased estimates of magnitudes. While for other applications, you often just don't really understand how the world works at all. I have some big software program, and there's lots of variables, and I don't know which ones cause what, and I don't know what are inputs and what are outputs. Same with the human body. I just don't really understand how it works. I have some idea that I start getting nervous, and I start to release some hormones, and then I start to sweat. And there's this causal pathway that my body goes through in response to stimuli, but I don't understand what it is. And so trying to discover the nature of causal relationships is really a very distinct subfield. And so I'm also not going to go into that today, partly because that's not what I work on, and also there are other people who can speak much more clearly to that. I've never done any applications in this area. I would say recently these literatures have started coming together. And all of these economics, statistics, computer science, engineering, all trying to come together. And I think really artificial intelligence and decision-making, personalized treatment policies, all of that stuff is unifying everyone in pursuit of a common goal. And so I would say the recent literature is really bringing causal reasoning, statistical theory, and modern machine learning algorithms together to solve important problems. So what are some of the themes of this literature? First of all, causal inference versus supervised learning. As I mentioned, supervised learning, one of the amazing sociology of science points is how having all these images and being able to hold out a test set has led to the advancement of science. If everybody can agree that if I do a better job telling cats and dogs by testing me in a test set, we can all agree what progress is, and we can make a lot of progress really fast. I guess my cautionary note would be that most problems aren't like that. Most problems, you can't tell if you did a good job or not. Certainly not that kind of precisely and objectively. As I said, I would spend 2 years arguing with people about whether I got the right estimate in an empirical paper, and at the end, half the people are unconvinced. So we just, the progress of understanding the impact of the minimum wage is very, very slow, even though there's a bunch of really smart people devoting their whole careers just to that. Other problems, you can go much faster. If I have 1 billion iterations of a game, I can see who won and lost, and I can really understand what happened and what wins and what loses. So the causal inference is different because I don't have an observed ground truth. Now, it turns out that we can make progress despite that. And what our literature has done is figured out ways to estimate objective functions, try to find model-free ways to estimate how well we've done. That's hard to do. It's noisier, more prone to mistakes, requires more assumptions than supervised machine learning. But nonetheless, we've been making good progress. And basically, the theme is we change the objective function. Another thing, as I said, sampling variation matters, and we care a lot more about uncertainty quantification. I would say that's a really important problem when I see firms going to apply AI. Some team builds this decision engine. They send it off to a loan officer. The loan officer looks at it. They see a recommendation, and they say, that doesn't make sense to me. You know, and nobody has told them whether that's an accurate assessment or not. And so they just sort of distrust the whole machine because sometimes they get crazy answers. And so we need to, as a community, put more emphasis on what are the places where this algorithm is just going to get things wrong. Maybe it's biased, maybe there's omitted variables, maybe it's just very uncertain, and really express that uncertainty quantification. That's been a big theme all along in causal inference. We do require theoretical assumptions and domain knowledge. And then one of the things I've also been finding very interesting is that tuning a model for counterfactuals is actually very different than tuning a model for prediction. You're going to choose different complexities of models, different functional forms of models. All of your choices will be different if you're tuning for a counterfactual versus tuning for a prediction. And indeed, if in a simple case like trying to understand the impact of changing price, it's very common for us to be able to, in a simple correlation, explain 95% of the variation. If I regress hotel occupancy on price, I can explain maybe 95% of the variation because the hotels raise the prices when they're full. But if I wanted to get the causal impact, I might have an R squared of like 0.01 or something, because it's just much, much harder to get the causal effects. The insights from statistics and econometrics. So what are some of the things that machine learning can learn? First, we usually start out by first thinking about identification and then estimation. We first ask, could we solve our problem with infinite data? That's what we call the identification question. And that's a very helpful exercise because it forces you to think about what in the data could possibly answer my question for me. And in many cases, the answer is, I can't answer my question. This data set just doesn't have the right kind of quasi-experimental variation to answer my causal question. All I can get is correlations, even with infinite data. We have a design-based approach, and then we want to do estimation. Now, where the big lift from machine learning has come is that now we have much more data, and we have many more covariates, and so machine learning has done a great job in figuring out how to do the best job and the most efficient job at making use of the data you have once you give it the right objective function. A few other themes. Regularization induces emitted variable bias. So if you have two things that are highly correlated, typically a model will choose one of them and not the other because they're providing similar information. But then that creates interpretability problems because, say, I have parents' income and parents' education. I might do a variable importance thing in a random forest and say, oh, parents' income is important, parents' education is not, which is like a silly conclusion because they're just highly correlated with each other. And most economic data sets and most firm data sets, frankly, all the variables about people are highly correlated with each other. And so I think people make a lot of mistakes in interpretation when they don't think about emitted variable bias. And it particularly challenges causal inference. Another thing, and this I'll have to flesh out in my more technical part, is that semi-parametric efficiency theory, which is a big literature in statistics and econometrics, it can actually be very helpful. And so we've been able to improve on the best known regret bounds for machine learning by bringing in the insights from semi-parametric efficiency theory and changing machine learning algorithms. And there's things we do called cross-fitting and orthogonalization, which basically make your models more robust to mistakes that you make in estimating what we call nuisance parameters. So if you're trying to get a causal effect, there's things like just estimating an outcome model, predicting what your outcomes would be, not your treatment effects. And for those outcome models, you try to residualize everything so that mistakes you make in that estimation are orthogonal to the problem you're really interested in. And it turns out that increases performance a lot, and it also improves the theory. Finally, I would say that exploiting the structure of the problem carefully for better counterfactual predictions. So a lot of the old people, and I'll call myself an old people since I started in computer science in the 80s, I do have a computer science degree before I abandoned it for economics. we get a little grumpy about all these black box algorithms. And to my economist friends, I'm trying to evangelize the black box algorithms. But those old folks are a little grumpy because we used to spend a lot of time thinking about modeling and generative modeling. But I would argue that if you're really going to do hard AI or human-like AI, we do have to go back to the models. And we're going to use the black boxes for components of those models, but we're going to use structure. Because you want to be able to make sensible decisions in states of the world you haven't seen before, and a lot of times that structure really helps. So in my supermarket analysis, for example, it just really helps to say, hey, we have these functional forms that tell us something about, like, if the price of this goes up, how are you going to substitute to other types of paper towels? How do I use the past behavior in a structured way? And those models have been super successful over decades, and I can beat the best kind of reduced form machine learning methods, just black box, by incorporating a little structure, and also using modern machine learning. But I put them together. OK. So now I'm going to spend some time going into some very specific models, and I'm going to start getting progressively more technical. So the first place, and this is where a lot of the emphasis in causal inference has been, about estimating average treatment effects under unconfoundedness. And indeed, for some folks in the causal inference land that aren't from social sciences, they think this is the only thing that we ever do, when I would say this is actually the least favorite way to do causal inference in economics. Nonetheless, and in fact, there's lots of people who think we should never do this, but I argue back to them, now tech firms are generating lots of the kinds of data that we would use that would satisfy the assumptions required for this setting to work. So the idea is that only observational data is available. That is, we don't have a simple, uniform experiment with A/B testing from the past. The analyst has access to data that is sufficient that has the part of the information used to assign units to treatments, and that's related to potential outcomes. So for example, a tech firm might be deciding, Facebook's going to show you something on the news feed based on a bunch of characteristics, and that data is logged by Facebook, the things that go into their algorithm. Now, their algorithm itself is a black box. So they typically, although in the ads we wish that they would if you're an advertiser, but typically firms don't actually log a probability of assignment. Like suppose the firm was randomizing what you were going to see, they typically don't log the probability because that would require taking a lot of draws from the black box, and that would be expensive, and why would you need to do that? You just do one draw and show the something to the person. But as an analyst, I can think of that as random and go back and look at it later. And of course, it's a computer algorithm, so whatever was used in assignment must have been recorded at some point. But the analyst doesn't know the exact assignment rule, and there was some randomness. In this setting, conditional on the observables, we have random assignment, but the assignment is not uniform. So people for whom I thought the ad would be effective were probably more likely to be shown the ad than people who were not. Contextual bandit data is another good example. If the tech firm is itself running a contextual bandit, or the political campaign is using a contextual bandit to say, I'm going to map your characteristics to the email I send you, then I would generate data like this. And then the question is, what's the treatment effect? So for an online ad, we could say ads are targeted using cookies. A user sees car ads because the advertiser knows the user visited car review websites. But there's still some randomness as to whether you saw the ad, even conditional on that. And so the interest in the cars is the unobserved confounder. But if the analyst can observe the history of websites visited by the user, which is the same thing that was used for targeting, then in principle, I can control for those things and do causal inference. So in this setup, we would formalize these assumptions as unconfoundedness, or it's also called ignorability. And basically what that says is that conditional on some covariates x, the potential outcomes that you would have received from seeing the ad or not seeing the ad were independent of the treatment. And so some of the things that could lead to randomness could be like running out of budget, or like a firm has a limited budget, and so they might only show the ads to half the people. Or competitors might be running out of budget. There's lots of things that could be leading to that randomness. This notation is the potential outcomes notation, and this yi of 1 and yi of 0 are these counterfactual outcomes. For each of you, there's a counterfactual outcome, what you would have had if you didn't see the ad, and what you would have had if you didn't see the ad. Even though I'm never going to observe both of those for the same person at the same time, those exist hypothetically. And so it's really important to write those down because that's what allows us to distinguish correlation from causality and to write down the objects of interest. Our object of interest, a treatment effect, would be the difference between your outcome if treated and your outcome with not treated. We need there to be enough randomness that for every type of person, there was some chance you saw the ad and some chance you didn't. So if there's people that just never get shown car ads, we just can't say anything about what would have happened if we did show them the car ad, so we should just throw them out. We can't say anything about them. We would have to extrapolate too much. But if there's people who had some chance of seeing the ad based on their characteristics, then we can put them in, even though it's not a high chance. And so the old literature from the 80s basically shows that it's sufficient to control for the propensity score. You don't have to control for the whole vector of x's, which it might be hard and high dimensional. The propensity score is enough. If I compare two people that had the same probability of being treated, then I can think of the treatment assignment as being as good as random. That's not completely obvious. It's a theorem. It's a paper. And you can find the algebra for all of that in my lecture notes. If you control for x well, then you can estimate the average treatment effect. And so there's a bunch of popular methods used to try to estimate treatment effects in that circumstance. So I can maybe do this best sort of visually. Here's a problem of a data set, and say the reds are treated and the purples are control, and here's a covariate x. And so what we're seeing is it looks like the treated guys are a little bit above the control guys, but it's a little hard to tell because it also looks like x increases outcomes, and it looks like there's a few more treated guys with high x's than with low x's. So x is a confounder. It's correlated with your outcome. Higher x makes you higher outcome. And it also seems to be correlated with the treatment assignment. People with higher x also were more likely to get the treatment. So there's a few different ways to try to do causal inference in this setting. The first thing you can do is just reweight the guys. So we can take the guys with high x's, and I did this by hand, so apologies, my blobs aren't perfect, that the guys with higher x's in the control group get weighted a little more than the guys with low x's in the control group. And if I do reweighting, then I can basically adapt for the fact that x was correlated with the treatment assignment, and I can then compare the weighted average of the purple guys, the control guys, and say, well, that's what would have happened to the treatment guys if they hadn't been treated. And then I would say, OK, if this in the reweighted average purple is lower than the reweighted is lower than the red average, then there's a treatment effect. So, and this is it turns out this propensity weighting has been very popular in machine learning because we've already had the idea of reweighting. It's very easy to take a machine learning estimator and reweight it off the shelf. And so this has been the most popular application of this causal inference literature in machine learning, is this kind of reweighting. Now, unfortunately, it turns out this is not actually the best way to do things, even though it's popular. It's conceptually easy. Another thing that you can do is you can do outcome modeling. So we could say, let me just actually take the control group, and I'm going to estimate the relationship between x and y. And then for every unit, I can sort of adjust for the impact of x. And once I've adjusted for the impact of x, then I can compare the treated outcomes and the control outcomes. This approach actually is implicitly used in a lot of the contextual bandit literature, like the linear Thompson sampling, the lasso versions of Thompson sampling in UCB. These algorithms implicitly rely on outcome modeling. They basically assume that you can run a regression and understand the impact of having different contexts and use that to draw inferences about which arm to pull. Now, that's going to work OK, but if you don't have a lot of data, then actually there's a lot more control observations at low x's. And so if this thing was curved, you might really screw up. Like if the purple average is a lot lower than the red average, the control guys have lower x's, you would really be extrapolating quite a long way to say what should be happening in the region of high x. And so if you have the wrong functional form, you can go way wrong, and that's why those models don't perform as well as they could. So the way that's tends to be the highest performing from this literature on causal inference is what's called double robust estimation. And then what we do there is we both reweight the data and use an outcome model. And if you think about it, once I've done reweighting, I'm not extrapolating very far. So if I get the slope of the line a little bit wrong, I'm not extrapolating very far. And so it doesn't really matter if I get the slope a little bit wrong, because my average for the treated guys and control guys is very similar. On the other hand, if I do the outcome modeling well, then it doesn't matter if I do my reweighting very well, because if I have a correct model mapping x's to y's, then I can adjust for the effect of x on y's, and I can control for the difference. But if you combine outcome modeling and reweighting, then you can make some mistakes in both and do a better job. And in a bandit, you never have enough data, especially early on. You're always in a data-poor environment. Therefore, you're never going to have exactly the right model. And so you're always going to get some benefit out of doing this. Now, if you did happen to have the right outcome model, then the reweighting will increase your variance. So there, in fact, is a trade-off. But in most real-world settings, you don't have the right outcome modeling, and so you do better by reducing bias. And this kind of doubly robust intuition, it turns out to be very important when applying machine learning to causal inference, because generally we have these high-dimensional models, and you do make a lot of mistakes. It's hard to estimate the treatment assignment policy. It's hard to estimate the outcome model. You can't control for everything. You have regularization-induced biases, and so combining the two, being more robust, makes you perform better. OK, so I'm going to stop here and take a break, and we'll come back at 3:40. Thanks. think people just filter in. So where I left off last time was talking about this kind of canonical problem, and I think it's like really the basic starting point of trying to think about a causal inference outside of the randomized experiment setting, and that's the setting with unconfoundedness. And so I would say the final recommendation out of this, and I have some formal results and a series of papers, is that actually you can make your optimal policy estimation or your bandits work better if you use doubly robust estimation. And so we have a paper coming out in AAAI, I guess in January, that illustrates this in contextual bandits, and then also I'll show you, if I get time, how that improves the best known rates from the machine learning literature on estimating optimal policies. And so, and again, this isn't, doubly robust is not my idea. It goes back a very long time. But I think the reasons that it works really well in machine learning settings in particular is that in high dimensional settings, we never get the models right. We think that it's a really big problem that we don't get models correct because we don't have enough data to really estimate the complete functions. And so this combination of outcome modeling, where the outcome modeling is basically trying to adjust for the effect of confounders on outcomes, and reweighting together can work better. So, and let me just go back, because actually somebody was asking me in the breaks that I went a little fast here, so I'm going to use this notation again. So let me just say one more time what all the objects are. This outcomes, yi of 1 and yi of 0, those are the potential outcomes. Those are the outcomes that you would have gotten. Yi of 1 is what you would have gotten if you were treated. Yi of 0 is what you would have gotten if you were control. If both of those were stamped on your forehead, then causal inference would basically just look like a supervised learning problem. The problem is there's a missing data problem that I only observe one or the other for any particular person. And it's not of course, if it was just missing at random, like in a randomized experiment, it's missing at random. So having data missing at random is not a problem. The problem is if the data is missing not at random, that is, the people who drank coffee or took the drug look different than the other people. And the wi is the treatment, xi are the features, and again, the unconfoundedness assumption is that if you condition on all the x's, these potential confounders, then after conditioning on them, the treatment assignment is as good as random. And again, I should mention, one reason this approach is sort of out of favor somewhat in social sciences is that what we found over a period of many decades is that people would apply this to observational data. They would kind of argue that they'd controlled for everything, but it was hard. They didn't have enough data to really do it well, and so they got different answers depending on which functional forms they chose. And so there was sort of a methodology war around this where some people said matching, some people said outcome modeling, some people said propensity scores. On any particular data set, you could get different answers from different methods. So I think the beauty that machine learning brings to all of this is that it gives you a systematic way to choose functional forms. And then also, if you adopt this sort of double robust type of approach, it tells you, you have many fewer decisions to make as a researcher. And using very flexible functional forms in a data-driven way to select them with the correct objective function can really improve things. And then finally, as I mentioned, I think in the modern digital world, it's actually more plausible that we might have a data set where the assumptions are satisfied. Where in the past, I might have said, oh, I'm going to try to figure out the effect of you going to college. And if I just control for enough stuff, you going to college is as good as random. And you might say, no, it's not. Two people who looked identical in terms of all the stuff I could observe in the census data, one went to college and one didn't, probably those people are different in some other ways. It's just not plausible that I've really controlled for everything relevant if I did it for an application like that. Or occupational choice or something. It just wouldn't be plausible. But if I'm thinking of a setting where I'm interacting in a digital environment and the treatments are being assigned digitally, then the treatment, if it's assigned digitally, then the X's must have been observed in order to make the treatment assignments work. Okay, so I'm going to kind of breeze through a few of the applications of machine learning, the way machine learning has come into this area recently. An early idea people had was to use machine learning to estimate propensity scores. And again, the propensity score, just going back a second, the propensity score is the probability that you're treated conditional on your X's. So if your X's show that you're very sick, you might have a high propensity to get the drug. If the X's show that you're healthy, you might have a low propensity to get the drug. So the propensity score is your propensity to be treated as a function of the covariates. If you go to a lot of car websites, you might be more likely to see a car ad than if you don't. And so this early approach was to estimate propensity scores and use those for reweighting. And I just gave one example, but there's actually been a number of people in the machine learning literature who've adopted propensity weighting in some form or another. For example, a group at Microsoft Research New York has done that a lot with contextual bandits, John Langford and co-authors. A second method is regression adjustment. So as I mentioned, that was then shown in the picture, kind of drawing the line. What you might want to do is try to just estimate, well, how do X's affect outcomes? How do your features affect outcomes? And if I can adjust for that, then I can adjust for the differences between the treatment and the control group and get a causal effect. So one of the early economics papers in this area, I mention it here, it's actually not the best method to use, but because they make this really nice point that it's very different to do supervised learning than it is to do causal inference. So in particular, what they suggest that you do is you use the lasso regression model to estimate two separate regressions. The first regression is the regression of the treatment assignment on the features. So this is estimating the propensity model. This is looking at the data and saying which X's predict who should be treated. Then a second separate regression model, which X's predict outcomes. Now, then what they suggest is take all of the X's that were not zeroed out in either regression. So if you were selected in either one, then keep them in. And finally, run a regression of the outcome on the treatment, Y on W, controlling for all these X's. Now, since Lasso is optimizing for goodness of fit, we know that you're going to be sacrificing goodness of fit, because if you do the cross-validation correctly, just the regression of Y on X and letting Lasso tell you which X's predict Y would be the best thing from the perspective of goodness of fit. So why would you sacrifice goodness of fit to throw in these other X's that don't even explain outcomes so strongly, but X's that explain treatments? Well, the answer is that if you don't control for confounders, you'll be biased, and you'll actually get the wrong answer. So in the example of a drug, there could be some medical sign that is important for doctors in assigning the drug. It's sort of weakly predictive of outcomes, but it's important for getting the drug, and it's indicative of being sick. And there might actually be a lot of weak predictors, and Lasso will zero out predictors if they're weak enough. So you might have a lot of weak predictors of being sick that are important for assigning the drug, and in aggregate are also going to affect how sick you are. But if you just do a predictive model of Y on X, you won't pick those up. And so the point is that for causal inference, we're not just concerned about predictive power, we're concerned about bias. We're worried that we might omit a variable that is a confounder. We're worried we might omit a variable that relates to both your treatment assignment and your outcomes, and that you would confound your causal effect. So this is a nice little kind of very easy to explain example that's a contrast between off-the-shelf supervised machine learning and causal inference. And it's really because our goal is different, and you can think about this as changing the objective function. Now, this is not the highest performing method, but it's just a simple example. So another method that's been fairly popular is to try to estimate the conditional average treatment effect and then average over the X's. And so there's a community, Jennifer Hill having one of the early papers here using BART, and that has been very successful in a bunch of, we have these causal inference competitions at this Atlantic Causal Inference Conference, and the BART-based methods have actually done really well in a bunch of competitions, especially in certain settings with signal-to-noise ratio being in a certain range. And so what she does is she's going to use BART to estimate the outcome model, and we're going to think about estimating the expected value of the outcome conditional on your covariates as well as conditional on the treatment. And if I can estimate that conditional mean function, then I can estimate, just take the difference between what that function would be when you're treated and what that function says you would be if you're not treated, interpret that as a causal model, and estimate the average treatment effect as getting the difference. So this would be an example off the shelf of outcome modeling. Now, in extensions, people have tried to bring in propensity weighting into the BART and so on as well. So the way that I would recommend, based on the statistical literature, is double robust or double machine learning methods. And so what this is going to do is take what's called an efficient score from this literature and statistics, and this is going to be related to kind of a theory about how do you efficiently estimate a parameter. And so in particular, in the case of the unconfoundedness, this is what the scores look like. And there's different ways to write the scores. So for every observation, I'm going to first figure out an estimator of the treatment effect. I'm just going to try to estimate a treatment effect model, a conditional average treatment effect. So I'm going to try to figure out what is the average treatment effect as a function of your x's. And I haven't told you yet how we do that. I'll come to that a little bit later. There's a variety of different techniques. I've been very into random forests, and so I would recommend you can use my generalized random forest package, which is available in R, but you can use lots of other methods for that as well. So you can think for every observation, you basically have a baseline estimate of the treatment effect for that observation. And then I'm going to adjust that treatment effect. And there's this kind of complicated algebra, but let me just say it in words because the algebra is a little bit hard to read. There's this term which is basically the residual of a regression of y on x and w. So I'm going to also separately build an outcome model, mu hat, which is going to be the conditional mean of the outcome conditional on the features and the treatment. And so then if it turns out that this observation was a treated observation, I'm going to weight it by the probability of it being treated. And if it turns out it was a control observation, I'm going to weight it by the probability of being control. And that's all that middle expression says. So basically what this score is doing is it's sort of orthogonalizing things. It's taking a residual, and this moment, mistakes I make in estimating these nuisance parameters, like the mu hat, which is not my main object of interest, are orthogonal to the moment. And what that's going to mean is that mistakes that I make, if I get mu hat a little bit wrong, it's not going to bias my estimate of the treatment effect. So this statistical theory, it's complicated, so I'm not going to be able to do it full justice. So I just really want you to kind of take the idea that for every problem that you look at, you can do a bunch of algebra and come up with a set of moments that you can use to estimate the parameter, and they're called orthogonal moments when parameters that aren't your parameter of interest, like I'm not intrinsically interested in estimating the outcomes, are orthogonal to your moment. And in particular here, that's also, we could say it's doubly robust, as I said before. If you get either the outcome model wrong or the propensity model wrong, you'll still get the right answer. And so in particular, if I use this approach, I'm going to get root-in convergence, even if the nuisance parameters converge more slowly, say at rate n to the fourth, which helps in high dimensions. So another thing that we're going to do here, which is not standard in machine learning, well, although it might be if you're using random forest, but isn't always used, is that we're going to use either out-of-bag estimates of the nuisance parameters, or we're going to use cross-fitting. So if we were doing a neural network, we might break the data into 10 folds, and for each observation, I'm going to estimate their nuisance parameters using data other than that observation. And what that's going to mean is that if one particular observation is an outlier, that observation might then draw up, say, the outcome model. And that would create a correlation between the outcome and the mistakes in these outcome models, in the mu hat functions. And so by using cross-fitting, I make myself much more robust, and that's actually important for the statistical theory here. And so what we found in applications is that using cross-fitting or using out-of-bag for the random forest actually really does improve the performance of these models. And I'll talk a little later about another example of a deep neural net implication of instrumental variables, where they also found that various types of orthogonalizing made a big difference in performance. A final method that I worked on actually gets rid of the assumption that you can even estimate the treatment assignment model. So suppose Facebook is using 3,000 features to decide whether you see an ad or what goes in your newsfeed. And suppose in my advertiser's experiment, I don't have enough data to really estimate that function well. So we use a programming approach to avoid actually estimating a propensity model, but the programming approach just directly tries to estimate weights and still gets double robustness. So I'm going to skip that math in the interest of time. Now I want to talk about instrumental variables. And this is something that you can use if unconfoundedness fails. And I would say this is actually a much more popular method in the social sciences. Now, a couple of years ago, I gave a talk about this at KDD back in Australia. And at that time, I asked how many people knew about instrumental variables, and almost nobody did. So maybe people have been exposed in the meantime. So let me ask again. How many people know about instrumental variables? All right, woohoo! There we go. Diffusion of ideas. So I'm going to go over them. I'll still go over them from the beginning, but then again, I'm going to try to talk about more recent research around these ideas. So the idea of an instrumental variable is it's a variable that is correlated with your treatment assignment. That means it's relevant, but it's independent of the potential outcomes. And so some examples of this, if your treatment is military service, suppose I want to know what's the effect of putting someone in the Army. Well, people who go to the Army are different from people who don't go to the Army, so I can't just directly compare them. But when we had the military draft for the Vietnam War, we could say that people with high lottery numbers were more likely to go to the war than people with low lottery numbers. And so the lottery number was randomly assigned. Now, rich people or people that had sore ankles or heels or things like that that had a high lottery number still didn't go to war. So the instrument didn't completely determine who goes to war. It just made you more likely to go to war if you had a high draft lottery number. There's a bunch of other examples of this. So in another one of my papers on random forests, we use the example from a famous economics paper about the impact of having multiple children on women's labor force participation. Now you're going to think, wow, I can't do a randomized experiment where I plop down babies on women. This is going to be pretty hard to understand. But it turns out that if your first two children are the same sex, that actually increases your odds of having a third child. And so having two children the same sex is randomly assigned, at least before we start genetically screening our babies. And so we can think about that as something that's orthogonal to your labor market outcomes. Things like your quarter of birth determine how many years of education you get, because if you're born right after a cutoff or right before a cutoff, that changes how much education you get, and so on. Even with things like advertising experiments or getting a drug, you can have things like non-compliance. So I can try to show an ad on Facebook, but Facebook doesn't actually show it. So I had a randomized experiment where I tried to show ads to these people and not to those people, but some other ad beat me out for some of the people. So what's random is my intention to treat, but not who actually saw the ad. And people might not comply with a drug trial. So those are some of the other big applications of instrumental variables. So let me actually skip over some of the details. There's something called a local average treatment effect, which can help get the intuition for instrumental variables. So suppose that the treatment and the instrument are both binary. So for example, the treatment is being in the military. Actually, no, that's not a binary. So the treatment is seeing an ad, and the instrument is whether you were assigned to the treatment group. We have some assumptions. Relevance means that the instrument has to be correlated with the treatment. Exclusion means that the instrument has to be random with respect to your potential outcomes. So it's not related to your treatment effect. And then something called monotonicity, which I'll skip over. Then the local average treatment effect is the ratio of two quantities. It's first the impact of the instrument on the outcome. That's like the reduced form. So it's like that would be just comparing the people I assigned to show the ad to the people I didn't show the ad. or it's the people I tried to give the drug to the people I didn't try to give the drug to. Then in the denominator is the expression which says, what is the impact of the instrument on the treatment? So in a sense, how much does being assigned to the treatment group increase your chance of taking the drug? And so the ratio of those two things is a treatment effect. Now, I can also do this conditional on covariates, and that's what I'm showing here. And that's going to be what's going to be more interesting from the machine learning perspective. I might actually have a lot of covariates, and I might be interested in heterogeneous treatment effects. So there's a bunch of different things you can do with machine learning around instrumental variables. So again, Viktor Chernozikov and co-authors at MIT had an early look at this using lasso models. And they basically argued that you could use lasso to try to figure out which instruments you should include in your regression. And so in particular, they would use lasso to select instruments when you have lots and lots of instruments. And so you can think about different scenarios where you might have lots of instruments. One example of this would be in a tech firm. So in the background, you're running lots of A/B tests. Say, Bing or Google's running hundreds of A/B tests at the same time. They are designed for different purposes, but each A/B test is going to have some impact on the user. And so I'll show you an example in a minute with ads, where we used A/B tests as an instrument for the ranking of the ads. The experiments weren't necessarily designed to change the ranking of ads, but they had an impact on the ranking of ads. And since which treatment group you were in was random, we could use that as an instrument. And so Viktor and his co-authors looked at this in a paper that looked at the effect of years of schooling on labor market outcomes. And the instruments were the quarter you were born, but also the interactions of those with lots of pre-treatment variables, lots of characteristics of people. And they got much more precise estimates. One of the experiments I ran when I was at Microsoft was, again, trying to look at the impact of being in higher positions for ads. So if I looked, here's two queries, iPhone and Viagra. These are two different queries that people would put into Bing, and each of these would show ads. And so if you just did a simple regression of whether the ad was clicked on the position effects, as well as the identities of the advertisers, it would look like there were really strong position effects. It looked like that being in the second position was about 2/3 as good as being in the first position, and then going down to the third position was about 40%, and the side position was like 5%. So it looked like the clicks were falling off really fast. But of course, this is not a causal effect because Bing isn't stupid, and they put the best ads on top. So an ad in the second position might get clicked less, not just because it's in the second position, but also because the ad is less relevant. So what we did is we used the identifiers for a whole bunch of A/B tests. And again, these A/B tests were not designed to do ranking, but they just had the consequence of affecting ranking. And we used those as instruments for the treatment, for the position of the ad. And what we found was that the position effects were much flatter than in the correlation. And of course, that's what you expect. In the correlation, there's two reasons a lower position would get clicked less. One is because it's in a lower position, and second, because it's a less good ad. So you expect the clicks fall off faster in terms of correlation than in terms of causation. And indeed, that's what we found. And separately, I ran a bunch of experiments randomizing positions at Bing and found similar results in a purely randomized experiment designed to look at this. And so I guess I would just say this was an example, circa 2008 to 10, where the search engine wasn't really taking this into account. So the click prediction model was just using the observational data and trying to control for ad effects and position effects, but wasn't really factoring in that there was this bias. And so indeed, we found the estimates in the click prediction algorithm were biased, and then working together with a group of people, including Liam Batu, really led a lot of this work to try to get more experimentation into the click prediction algorithms. Okay, so another thing we can try to do is to look at heterogeneous treatment effects. So we want to understand for whom is a treatment effect large. And so I'm going to illustrate this with two different approaches. One from a paper of mine with Julie Tibshirani and Stefan Wager that's just coming out in Analysis of Statistics, and another that was by a team that was at Microsoft Research at the time, including Matt Taddy, Greg Lewis, and Kevin Leighton Brown from UBC. And that's using neural nets. So I'll start with the neural net approach. So first of all, here's a little causal diagram showing the instrumental variables application that they were looking at. So they were interested in trying to understand the effect of price in this example. And so the goal is to understand, say, for a firm, what happens if they change their price. And by the way, this was part of a project that this team was working on to try to commercialize some machine learning algorithms that were designed to help firms make decisions, with the idea that a lot of firms want to do causal inference about things like prices, not just do prediction. So the causal diagram shows that there's a bunch of things that affect price. So in the firm's historical data, there might have been shocks, things that caused the firm to change the price that were also related to outcomes Y. So the firm might raise their price in a high demand day. And that E, that would be the unobservable, that's not observed to the analyst, but it was the thing that caused the firm to both raise the price and have high demand. There's also some covariates X. These are sort of just characteristics of the context. And then Z are the instruments. And so Z, for the case of price, they might be cost shocks. They might be randomized experiments the firm ran if it was kind of more of a tech firm or more pricing online. And Z would be something that's affecting the price that's not related to demand. And so again, in economic applications, historically, we looked for things like cost shocks that would cause firms to change the price for reasons that were unrelated to demand. And so the key thing is that the Z is excluded from the outcome relationship. So Z is not directly affecting it's not directly related to say the demand for the firm that day. And so what that means is that I can write the expectation of outcomes conditional on X and Z in a very particular way. Here I'm writing it as an integral. And I'm saying, OK, there's some function g of p and x, and that's telling me basically something about how changing price is going to change outcomes. And there's also, in the historical data, there was some distribution of prices. And prices tended to be, on average, different in different contexts X. And prices were also different with different z's. But the key is that the z is not in the g function. That's the formalization of the exclusion restriction. Z is something that's shifting prices, it's shifting the price distribution, but it's not actually affecting the overall demand relationship. And that exclusion restriction is what allows you to actually learn about the effects of price on demand. Without that, you don't have a good way to learn that. And so what they argue is that we can use neural nets to solve these two different parts of the problem. First of all, I can just solve the problem of figuring out how do X and Z predict Y. That's a prediction problem. That's understanding what that whole integral looks like. But separately, I can also use neural nets to figure out how do X and Z affect price. And then I've got this integral that says how they fit together, and I can basically try to invert that. Now, economists have thought about this for a long time. I'm citing here a paper by Newey and Powell from 2003, which was actually written in the early 90s. I told you we take 10 years to publish our papers. And so this approach had been used for a long time. It's just that we never operationalized it very well in high dimensions. We had great theory, but no practical algorithms. So the typical way that we would have done this in economics is we would just assume everything was linear. And then if everything was linear, we could just run this with regressions, and inverting this would be very easy. Because if everything was just linear, then my demand function would just be some parameter times the price. I could just pull that out of the integral. So if I could just estimate how Z, the instrument, affects prices, and if I could just affect how Z affects outcomes, just take the ratio, and that would be my estimate of tau. So that would be a very easy thing to do, and that's called two-stage least squares. And again, that's a staple of undergraduate econometrics. We then tried to make this more complicated with sieves and other types of nonlinear functions, but it just never worked very well, so nobody ever adopted it. So now what this paper DeepIV suggests is let's go back and actually target this loss function directly. They're going to change the objective function, but they're going to use neural nets to basically analyze each of these functions and then try to find the demand function that actually minimizes the loss function. So they've turned this causal inference problem into 2 generic machine learning tasks and applied them. So they actually, the earlier IV regressions or things that I did in the late 2000s, they came back and did a much more thorough job with this same application of trying to understand the impact of position on the click-through rate at Bing ads. And so not only now were they trying to estimate the effect of position, but they were trying to understand the heterogeneous effects. So some kinds of queries are brand queries and some are not brand queries. Or some are navigational queries and some are not navigational queries. And in addition, some queries are for websites that are very popular and other queries are less popular. And so they use this deep IV approach to try to look at the causal effect of position and see how it changed with all of these different covariates. And again, they use the A/B test IDs as instruments. The A/B tests were not designed to shift the ranking, but they just had that as a consequence. Each particular experiment only had a small effect, but there were lots of experiments. So they basically had lots of small natural experiments in the data. And for example, they found that for off-brand queries, the position effect was fairly constant with the website rank that was clicked on. But for brand queries, they found that the position effects were much stronger for unpopular websites. So that these low numbers mean that the relative click rate of, say, being in the second position was much lower than being in the first position. But if you were a very popular brand website, then being demoted to the second position didn't do much to your click-through rate because people who were looking for you would click on you anyways. So manipulation, in some sense, would be less effective in reducing clicks for brand queries. Okay. And actually, I have a PhD student, actually an undergrad student who's now applying for PhD programs who took my class, and he did another nice application of deep IV in genetics. And there, you can think about your genes as being random, and they're affecting the probability of you getting a disease for reasons other than behavior and what you eat. And so he made a nice application of deep IV to try to understand the effects of disease and treatments. So that was a nice application of this technique as well. So now I'll tell you about one of the methods that I've been spending a lot of time on, which is generalized random forests. I know random forests seem very, very old-fashioned to this audience, but nonetheless, they still work pretty well out of the box. And they turn out to have really nice statistical properties. And so we've been actually getting a lot of traction on them in social sciences because we're able to do things like prove asymptotic normality and get confidence intervals, which are still somewhat elusive for neural nets, although there is progress being made on that, including by some colleagues at Chicago. So the basic idea of what we're doing with generalized random forests is we're trying to think about doing local estimation. And we basically reinterpret random forests as a way to generate neighborhood functions. And so we say, if I want to figure out the treatment effect for you, I'm going to build a bunch of trees, and people who are more likely in the same leaf as you are going to be people I consider to be your neighbor. I'm going to label them to be more like you. And so then I'm going to run analyses like instrumental variables, but I'm going to run them separately for each covariate value, and I'm going to do a local analysis weighting more heavily the people that are similar to you. There's a lot of computational work that goes into this, particularly because we want to make sure that we're looking for heterogeneity in parameters. So our goal, again, is treatment effect heterogeneity, not predicting outcomes. And so we optimize our random forest splitting rules for the heterogeneity in the parameter estimates. And so we have imagine a setting where we have a parameter of interest, theta of x, that would still be like the treatment effect. And we have some moment conditions, or maybe maximum likelihood equations, that tell us how to estimate the parameter. But we want to do it locally. We want to make it a function of x, and we want to do that very flexibly. And so this moment depends on our parameter of interest, theta. It also depends on nuisance parameters. And so in the case of IV regression, there's a bunch of different ways you can write down how you estimate IV, but one way is to write it down in terms of a moment condition where you multiply, you want to set equal to 0 the product of the instrument and the residual of a regression of the outcome on the actual treatment assignment. And so those moment conditions can then be estimated locally as a function of x. And so the way we would operationalize that is that for each target x, we would create a weighting function alpha, and we would set the moment, we would try to solve for the parameters that set the moment condition equal to 0, but we're going to weight more heavily the nearby x's. And so what do I mean by nearby? Well, I'm going to generate a bunch of trees. Each tree is going to be a partition of the covariate space, and I'm just going to take the frequency of being nearby as the weight that I get in this weighting function. Now, there's a few more details, because in order to get asymptotic normality for this, we actually need to use sample splitting. So in particular, we use subsampling to create the trees, and in fact, we use 2 samples for each time we create a tree, 1 sample to create the partition, and then another to select weights, because we're trying to be careful that we don't let an individual's own outcome influence the weights that it receives. So in this paper, we establish asymptotic normality of the parameter estimates and provide confidence intervals. We also recommend orthogonalization, and we have some reasonably high-performing software on CRAN in R called Generalized Random Forest. And if there's any students in the audience, we have lots of people contributing to this project, and we welcome contributors. So in this package, we'll do things like quantile regression, regular causal inference under unconfoundedness, randomized experiments, instrumental variables. It can also deal with clustering and so on. We've also been working on trying to deal with some known weaknesses of random forests, and in particular, in a lot of the economic applications I look at, there's some smooth relationships. Like you might have, your outcomes might be increasing in income, or if you think about a tech firm application, there's a lot of monotonicity. People who are more active are going to do much more of lots of other things. They might also have higher treatment effects. And so the problem with forests is they make these kind of rectangles, and they weight everybody equally within a rectangle. Now, when we average over the rectangles, we're going to get smoother weighting functions, but we still aren't really accounting for the fact that if someone's on the boundaries of a rectangle, then they might be fairly far from a target observation. So together with a student of ours, Rena Freeberg, we wrote a paper called Local Linear Forests, and this is motivated, again, by some work that's been done in the statistics literature, where what we do is we adjust for observations within a leaf being far away. Another way to think about it is we run a local linear regression at each point, weighting using the random forest weighting kernels. And so we see that where a regular random forest would fit a step function and have a hard time estimating a steep slope in a small data set, by using these local linear adjustments, we get much smoother effects. So we apply this to causal inference. We looked at this randomized survey experiment where there was done by the government, the big social survey that's done every year. And for a period of years, they randomized asking people one of 2 questions. Some people were asked whether they wanted to provide assistance to the poor, while other people were asked whether they liked welfare. Now, those are actually the same thing, but people in the US don't like the word welfare. It's been poorly branded by conservatives. So if you look here, we see that the treatment effect is actually much higher for conservatives than liberals, and for rich people than for poor people. But the normal causal forest kind of flattens things out near the boundaries, while the local linear forest makes things smooth. So let me now skip to the last part. I want to talk a little bit about structural models and discrete choice models in particular. And this is an area where I've been working together with David Bly to try to put together some modern machine learning methods from Bayesian inference, variational inference, with traditional econometric structural estimation. So this is a problem of a firm trying to estimate the impact of changing prices. And so the way that these have been modeled, and this actually, Dan McFadden worked on these models in the early 1970s and won the Nobel Prize for this more than 10 years ago, maybe 15 years ago, for this work. And he was actually motivated by a transportation problem. So he was trying to say, counterfactually, what would happen if they expanded the public transportation in San Francisco? And so he really needed to understand the welfare and use revealed preference to understand that. I'm applying this type of model to supermarket, which is a very common application in economics and marketing, where I have scanner data from supermarkets. So what we do is we model first that each person has a mean utility. So user U with product I and time t has a mean utility for a product. It might depend on the observed characteristics of the products, and it's decreasing in price. So the higher price, the less I like the thing. And then I'm going to say that my utility is equal to my mean utility plus some idiosyncratic error. And it turns out if that's an extreme value error, if it has a particular logit functional form, then we can write the probability of you buying, that user U buys item I at time t in this pretty multinomial logit format. It's just e to the mean utility of the item divided by the sum of e to the mean utilities of all the items. And so sort of part of the Nobel Prize winning work was relating this statistical model. Lots of people run multinomial logits, right? But relating the multinomial logit to a user utility model. And then he also did more work looking at some of the unpleasant assumptions that come out of just having this simple model, and did various generalizations that made it look more realistic. Now, if you just have a cross-section, you can kind of figure out something about overall price sensitivity. But if you have a panel of people where you see their shopping data over time at the store, you can actually learn an estimate for each person of their price sensitivity as long as the prices are changing over time. And so that's what I do in a series of papers. I have some on shopping data, and we also have some using mobile location data for people going to lunch. So we have a large data set where we observe from people's mobile phones where they are during the day, and we see where they work as well as where they go to lunch. And for each of these, we do a couple of things. We first bring into this very simple model matrix factorization. So we look at lots of products, and instead of trying to estimate, for each product what its utility is, we actually use matrix factorization techniques to improve efficiency. We also are going to be we're going to use modern computational techniques. So historically, marketing people used Markov chain Monte Carlo, but that didn't scale very well, and so we're going to use variational inference. And then we're also going to do some things to like for the case where we use data about the product hierarchy, we're going to study products where people only choose one of them, and so we're going to use that fact in our estimation. So in our model, our mean utility, instead of having kind of just fixed coefficients, we're going to have a factorized mean utility that's going to be latent, and we're going to try to learn a latent factorization of the mean utility. And we're also going to try to learn a latent factorization for the price sensitivity. So each user will be characterized by a vector of mean preference parameters as well as a vector of price parameters. And then each product will be characterized also by a vector of parameters. So we'll learn that lettuce is like tomatoes, and if you're price sensitive for tomatoes, you might also be price sensitive for lettuce, and we're going to learn that from the data. But we're going to have this nice functional form, and this functional form, this multinomial logit functional form, has the property that it's going to tell us, like, if I pull one of the items out, like if I pull out your most popular item, it's going to tell us how you substitute to other products. And so the model will actually tell you the consequences of raising a price of one product on the demand for all of the other products. And that functional form turns out to work very well in practice. Now, one of the modifications we needed to do was to model just whether you choose the product at all, because on most shopping trips, you just don't buy paper towels at all. And this is called nested logit. That was one of the things Dan McFadden got his Nobel Prize for. And so now we have a factorization version of the nested logit, where we also factorize the probability of not buying an item at all. And there's this nice algebra that shows how you relate all of these things, and it simplifies the computation. So I just want to kind of close off with two kind of interesting things that come out of this. First of all, one of the things that we did differently in this paper is that because we had lots and lots of price changes in the data, we actually tuned our model for the counterfactual. So in particular, instead of just tuning for the log likelihood of goodness of fit overall, we instead tuned for, made a held out data set of weeks that had price changes. And then we selected the model that did the best at predicting the change in purchase probabilities from price changes rather than the ones that predicted best on average. And it turned out that those were different models, and that's important. And so what we did, this is just one of our goodness of fit tables, we looked at what happens in a week where another product in the category changed prices. So like if one brand of bottled water increased its price, we looked at the goodness of fit of predicting what happens to the other brands of bottled water. We also do the same thing for out of stock and own price changes as well. And so we find that our model, of course, I'm showing you the picture, so of course our model does best. And we compare it both to traditional economics and marketing models, as well as to what happens if we take a reduced form machine learning model, we just throw a big factorization at things, take the parameters out, and stick them into an economics model. And it turns out that taking a big machine learning model, just getting reduced form predictions that don't use any structure, and sticking those predictions as covariates into classic economic and marketing models does a lot better than not doing it. So if you were trying to scale to a large tech company, that might be a good intermediate solution relative to ours, which is more computationally expensive. And then the last thing I want to show is just what you can do in terms of if you have this counterfactual model. So this counterfactual is about personalized pricing. So once I have estimated every individual's price sensitivity, I'm going to say some people are more price sensitive than others to a particular product, and those will vary across products. So I can do a counterfactual where I imagine targeting a certain set of people with coupons. And we compare the performance of our model with other models in terms of how much personalization helps. And by using this rich factorization model relative to what the traditional economics and marketing models, we get much more personalized estimates, and therefore we can get a lot more benefits from personalization. And in our paper, we also go through and we validate those things by looking at held out data and show that indeed the people that we think are most price sensitive tend to be more profitable on days where they get prices that are more appropriate to them. So I will stop here and take questions. So thanks very much. Yes, so if anybody has questions, please come up to the microphone. While people are coming up with questions, I'll just say I'm going to make my slides available. I think actually the easiest place, I'm not sure I can get them on my website by tomorrow, but if you Google Susan Athey AEA Machine Learning, that's AEA is the American Economic Association, I have a little drive there where I keep all my lecture notes updated, so you can find a link to the Google Drive, and I'll put them there for tomorrow. Yeah, question?
Hi, thanks for the talk. So this is kind of just a practical question for like internet companies. Why can't they just know the propensity of the treatment? Like they're the ones making that decision. It seems like it's easy to just have a model that outputs a probability of the treatment and then record the probability along with the treatment.
Yeah, so the question was, why don't the tech firms just keep the propensities? Well, so the causal inference folks lobby for that quite heavily, but it's actually, I'm actually on the board of some companies that do a lot of advertising, and we have lobbied tech companies to provide the advertisers with those propensities to help us evaluate experiments that we run as well, or use observational data. So the problem is it's expensive, because usually you can think of like, if there's randomness going on, if you show up at Facebook, you know, they're just going to kind of sample from a black box and figure something out. If they were going to get a probability, they might have to draw 100 samples from the black box. And if it's a black box, they can't really write down the probabilities. But they could do something like offline that would be approximate. And you know, so we wish that they would keep track of them more often. And maybe with enough lobbying, they will. Sometimes they do.
I guess I don't understand why it's a black box that outputs a decision instead of a probability of a decision. Because like normally in machine learning, we output a probability distribution over what decision the classifier is going to make or something.
I mean, not always. So not always in these tech systems. Yeah. So I mean, and you might like for the Bing search engine, you might be like 200 classifiers, but then they go into a final thing, and then out pops a page. So there's actually not a probability distribution for all the pages that you could have showed.
Thanks.
Yeah, go ahead.
Hi. I have a question regarding local linear forest and random forest that you have used. Is there any incremental learning behind choosing the number of local random forest?
Yeah, so I think we have that. I would say that's not fully solved. So we would suggest that you might do some pre-processing to figure out which covariates go into that regression. We actually use in the software we use a ridge regression to regularize.
Okay, and it's not very complex because random forest by themselves, that is complex, and finding there's a lot of hyperparameters that we need to fix. So when you have some local random forest, there are huge parameters that you need to fix. So it's not a little bit complex model.
Yeah, so the tuning makes more of a difference. You're absolutely right, and we are working on tuning algorithms, but they work sort of well, but not great.
Okay.
So and they're computationally expensive. So yeah, you give something up.
Okay, great.
Yep.
Hi there. So you gave a pretty strong recommendation for doubly robust methods.
Yep.
And you also mentioned the Atlantic Causal Inference Conference competition. And my reading of the 2016 results was that modeling outcome alone did extremely well. And I was interested in just your thoughts on that result and how to interpret it.
Yeah, so I think a lot of this really depends on the data generating process. So if you can model outcomes well, if you have enough data to model outcomes well, then the propensity weighting just increases the variance. And so I can absolutely generate lots of examples where that can happen. But I guess I've been playing a lot with bandits lately where we don't have enough data. Like in the beginning stages of a bandit, you definitely don't have enough data. And so the outcome models kind of are not good enough. But I think it does depend on the setting. And the small data literature actually has the same message. It depends, which is a little bit sad. But I still feel that as we've moved to higher dimensional methods, I think that it pushes us more towards doubly robust and the orthogonalization. And then some of the results we have theorems about estimating optimal policies, and we have good regret bounds. We have the best regret bounds are with doubly robust, and we don't think we could get the same regret bounds otherwise, although we haven't proven a counterexample. So I'm becoming more convinced of that, but I think any particular competition, anything can win. Okay, last question, yeah.
Hey, thanks for the talk. And I'd like to ask you a question about the interpretation of the results we got from the use of many IV, like many A/B tests, because we know that by using IV, we basically estimate a local average causal effect. If we have so many IVs, then how should we interpret the final estimate?
Yeah, that's a great question. So there's a lot of subtleties with using instrumental variables, and if there are unobserved, there's some unobservables that affect your treatment effects, then it can be very complicated to interpret your results. So actually, my husband's Hito Imbens, who's done a lot of work on local average treatment effects, he coined that term, and I tried to get him to work on this problem 10 years ago, and he didn't want to work on it for just the reason that you said. He said it would be too hard, too messy, and then other people just assumed the problem away and went forward. So yeah, instrumental variables can give very messy interpretations, and that's just a problem I don't have a solution for.
I see. Thanks.
All right, thanks very much.